Am I audible?
Yes, sir. Audible. Yeah.
Okay, thank you.
Yeah.
So, good afternoon, everyone. Welcome to week 10 of the live session on the course Finite Element Method. I'm your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IT Madras. So, in the last 9 weeks, we have almost completed the topics regarding the formulation in bar element, then beam element, then we saw the trusses, we saw the frame members as well, and solved a lot of numerical examples in these applications, in these structural applications. So last 9 weeks were all about structural aspect of this finite element method. So in this today's lecture, that is the week 10, we will see how we can put all these applications into a single one-dimensional boundary value problem, and how that single one-dimensional boundary value problem can have application in other fields as well, like the applications in fluid flow, applications in the heat transfer, and applications in column buckling and other things as well. So we now want to give a concise picture of everything what we have studied in last 9 weeks in the form of a generalized, or we will generalize our study of last 9 weeks into one formulation, and we'll see how that formulation will be beneficial for us to solve the problems in other fields as well. Because for your information, finite element analysis is not used only in civil engineering, especially in structural engineering. It is used in each and every domain of engineering, as well as its allied fields, like it's used in biology, it's used in medical applications, it is used in mechanical engineering, in applied mechanics, everywhere you see it is used in computational fluid dynamics. This finite element method is everywhere. So today we will be seeing a generalized picture of what we have studied in last 9 weeks. So starting with today's topic is general 1D boundary value problem and its applications to other fields. So if we see in the from the last 9 weeks, we can see that a large class of practical one-dimensional problems is governed by. So most of the problems that we saw in the last 9 weeks, we saw that all of them were linear in nature. They were linear in nature, and most of the problems were second order differential equations. Okay, differential equations, second order differential equations. So a linear second order differential equation, let us put a generalized form to that. Let me write a second order differential equation that is linear in nature, that can be of the form like d by dx of uh, k of x dt by dx plus p of x times t plus q of x, q of x is equal to 0. You people can easily see that this is linear in nature, because here, for example, if the field variable is t, so field variable t and its differential are not coming in the product, like we don't have t times dt by dx. That term is not present here, otherwise it would have been non-linear in nature. So this is a linear differential equation and second order, because there is double differential present, say second derivative present, that is d2 by dx square is present. That's why it is second order differential equation. So we can say that most of the problems that we studied had a boundary value problem that can be generalized in this form: d by dx of k of x dt by dx plus p of x times t plus q of x is equal to 0. With domain, we saw that all of the problems were having some domain like x naught less than x, less than x of L. Okay, this was the domain of the problem. Here I will define these terms k of x, p of x, and q of x as follows, where I can say that k of x, comma p of x, comma q of x, q of x are known coefficient functions. Okay, these are known coefficient functions. Known coefficient functions of x, and what is important is our main candidate is t of x, that is our field variable. Okay, is some field variable. I hope by this time you must have got the idea of what I mean by field variable. Is that like in bar problem, we saw that the axial deformation or the axial displacement u was the field variable. Uh, in beam bending problems, we saw that transverse displacement, that is transverse displacement in the downward direction or upward direction, that is v was the field variable. So here we are generalizing it with t of x as some field variable. Okay. So this boundary value problem will be having some appropriate boundary conditions as well. So for example, if its boundary conditions are specified like this, boundary conditions are specified. We can have boundary conditions at x is equal to x naught. We can have boundary conditions at our field variable is given as equal to t naught, at x equal x naught, t is equal t naught. It is a specified constant. Okay, so if we see that specified constant, and if we see the nature of this boundary condition, this is essential boundary condition. Okay, essential boundary condition. Or we can have at x equal to x naught, we can have another value specified. We can have this whole value specified as k naught dt by dx, k naught dt by dx plus alpha naught uh, t plus beta naught. Okay, this can be specified, that will be equal to 0. This natural boundary condition can be specified. Okay, okay, where I can write k naught to be equal to k of x, but at x equals x naught, k of x at x equals x naught. Okay, I hope you are understanding my terminology. And alpha naught and beta naught, alpha naught comma beta naught are constants. You remember these terminologies. Okay, and we can have boundary conditions specified at x equals extreme xl, that is the extreme of our domain xl. We can have there as well t is equal to tl, some specified constant. Okay, specified constant, and it again will be essential boundary condition. Okay, it will be essential boundary condition. Or we can have same like this, we can have kl dt by dx plus uh, alpha lt plus beta l. I hope few people are connecting. Natural boundary condition, you are connecting above parts and below parts. Okay, natural boundary condition, where I can again write k of l is equal to k of x at x is equal to xl, and alpha l and beta l are constants. I hope up to this point this is clear to you. Now what we have to do is that we can do the same procedure for this 1D boundary value problem. We can go through whole procedure of finding the functional using Rayleigh grids method. or variational method. That functional we can then minimize with respect to our unknowns, and we can get the element equations. That is a very rigorous process that I have taught you in almost 3, 4 lectures. I taught the same thing in you in Rayleigh method or in variational method. I taught the same thing in bar problem as well, in truss problem as well as in beam bending problem. I hope by this time you people would be able to deduce the functional for this, equivalent functional for this boundary value problem. So directly, I will be writing here equivalent functional because we have to follow the problems. That's our main goal. So I will not be wasting my time again showing you how we obtain this equivalent functional. Okay. So the equivalent functional, there I am writing the appropriate appropriate functional for boundary value problem for BVP boundary value problem is, so we can write the functional as I, it is a function of t, I of t to be equal to, it's a very long term integral of x naught to xl, x naught to xl, it is k by 2, it's same k of x, dt by dx whole square minus p by 2, that's p of x, same p of x, t square minus qt d of x. And then we have boundary terms. Because of boundary conditions, we will be having boundary terms 1 by 2 alpha L t square plus beta L t at x equals xl. Okay. Same will be minus times 1 by 2 alpha naught t square plus beta naught t at x naught. Okay. So you people can see that there are equivalent functional for this. One-dimensional boundary value problem can be having this following form. So we can now perform the same finite element formulation where, and we can use two-noded element with nodes 1 and 2 of length L, same field variable node values as T1 and T2, and then can obtain the element equations for it. I will be directly writing the element equations for this problem. Okay. So here in what we can do is that we can use the same formulation for this. We can use, now we can use a linear finite element. Finite linear finite element for boundary value problem. Okay, we can use a finite element of this form. Okay, it is having two nodes, node 1, node 2 of length L, having nodal values T1, T2, same formulation that we did. It's one node at x1 and x2. Then we can get the same stiffness matrix and then the load vectors and other things. I will directly write all those things. So it is stiffness matrix is composed of three different things. It's K, that is stiffness matrix. K is equivalently written as K K K K plus KP plus K alpha. Okay. Sorry, I have to write a little bit. bowl. Okay, this is this is k to be equivalently written as k plus k p plus k alpha, and its total value is given as that is k by l, length of this element, minus 1. Sorry, this is not minus 1. 1 minus 1 minus 1 1 plus pl minus 1 by 3 minus 1 by 6 minus 1 by 6 minus 1 by 3 plus minus alpha 1 0 0 alpha 2. Okay, and its R matrix R is given as RQ plus R beta, and its value is given as its same Q of x, that's Q 1 by 2 1 by 2 plus beta 1 beta 2 minus beta 2. Okay, and you know that field variable t as to be equal to t1 t2 nodal values. Okay, nodal vector. Now we can use the same formulation in different applications. We will be using this formulation with different applications to see solve our problems. Okay, so if we will go to the fluid flow problem, if we see how fluid flow happens. So for example, we have two parallel plates, like I will write applications. Now applications of this general one dimensional boundary value problem. Fluid flow between flat plates. Okay, between flat plates, lubrication problem. Okay, okay, we have lubrication. For example, consider this one plate. Okay, this is fixed plate. Okay, fixed plate, and this is x-axis, fixed plate, and we have one more plate here that is free at the top. Okay, we have a fluid flow y-axis, and the fluid profile within this is velocity profile of the fluid is like this. Okay, so obviously we will be having maximum velocity at this point, that is the top surface, and it will be gradually decreasing. And it is u of I. Okay, and the distance between two plates is h. Okay, height h. And here the velocity of the flow is u at h is equal to capital U. Okay, this is the maximum flow velocity that fluid can have. Okay, this is flow between two plates. Okay, one more thing I forgot to note is let us denote P to be equal to pressure of flow, mu to be uh, fluid viscosity, rho density, fluid density, and U to be horizontal flow velocity, okay, or fluid velocity. Okay, and we are one more thing considering here, it's a laminar flow and the gradient of the pressure gradient is constant, that is dp by dx is 0 and no variation is in y and z direction. It's a Newtonian fluid, so its shear stress will be given as, one more thing, assumptions that we are making is, first is it's a laminar flow. Second is gradient of the pressure, that is dou p by dou x, constant. Okay, this is constant and there is no variation, in y and z directions. Okay, so we know that shear stress tau x y will be given by mu times du by dy. Okay, we know it from fluid mechanics because shear stress is related to velocity gradient. So for no slip boundary condition, no slip boundary condition, so there is smooth flow of the fluid within the between the plates, and there is no slipping of the fluid. So for that, uh, mm, velocity at bottom is equal to 0. That is at y is equal to 0. Okay, and velocity of fluid is equal to capital U, and that is at y is equal to h. These are the boundary conditions. Okay, you have to keep in mind. Okay, these are the things. So the governing differential equation can be considered by considering the equilibrium of a very small element with sides dx, dy, and dz. And we can see that the forces acting on that small element, we can calculate the forces acting on that small element and then see how the variation will go. So for example, if we consider a very small element like this, we are in that direction, like this is, sorry, this is xy direction, and z direction is coming out of the paper, and we are considering unit width in that direction. Okay, so this is only dx and this is dy. Okay, dx and dy, so for example, if pressure Px is equal to P is acting on this face like this. From this face, it will be Px plus dx. Okay, obviously P of x plus dx. Okay, pressure. So it will be equal to P plus variation of dou P by dou x dx. Okay, it will be like this. And if shear stress uh, tau yx is acting along this face, and it will be having a variation of addition of along some addition along y-axis, tau yx plus tau yx by tau y dy. Okay, hope you got this point. Okay, if we if we see the equilibrium in the x direction and write the forces in x direction, what we will get? So the same element, we will write summation of f of x to be equal to 0. We will see that. So this is pressure P acting on this phase. So it will be P times area will be dy times dz. This is dz, no? It's like this. So dy times dz will be the area of this surface, and pressure is acting on that. So we have one force P times dy times dz acting in this direction. Okay, and then same for this one is also acting in the same direction, but here it will be dx times dz, because dz is like this, dz. Okay, so it will be uh, tau yx plus tau yx divided by tau y dy times dx dz, and then other things will be the minus. This is opposite, this is opposite of this will be minus, and this will be minus again. This will be minus times tau, sorry, tau yx dx dz minus p plus dou p by dou x dx times dx dz. Okay, dy dz, sorry, dy dz. Okay, it will be equal to 0. When we will solve this equation will boil down to d tau yx by dy minus dp by dx is equal to 0. We'll have this relationship. Okay, but this tau yx is already given as mu times du by dy. Okay, we know that, so we will substitute this here. Okay, we will get this to be equal to d by dy of mu times du by dy, dy minus d p by dx is equal to 0. Okay, if you see that we got the governing differential equation for our boundary value problem, that is the fluid flow between the two plates. So if we compare this with our governing differential governing boundary value problem like this, let me compare it with it. Okay, so I am seeing you people to compare it, comparing the two, comparing the two. If we compare these two, we will see that Uh, the solution of this uh, fluid flow problem will come out to be mu by L, or the element equation, not the solution, element equation. Mu by L 1 minus 1 minus 1 1 times U1 U2. That's already the field variable U1 U2. U1 U2 is equal to minus dp by dx L times 1 by 2 1 by 2. So we got our element equation for our fluid flow problem. Okay, this was very simple, very easy, because we already had deduced governing differential equation and it is solution. Okay, so once this velocity profile is known, no, we got all the velocity at all the points. We can then easily compute the velocity pattern within the fluid depth, and as well as gradient of this velocity, and the shear stress as well. So the formulas for them are as follows. I will write directly. So uh, first, this velocity pattern u of s can be calculated as to be, here again this n1 and n2 are the shape functions, n1 n2 u1 u2. Okay, so it will be equal to, we know that shape functions is 1 minus s by 2 times u1 plus 1 plus s by 2 u2. Okay, this one. And the variation du by dy will be given as 1 by L minus 1 1 u1 u2. Okay, this is very easy. And shear stress will be simply given as tau xy is mu times du by dy. And it is mu by L, if you connect above points, mu by L minus 1 1 u1 u2. Okay, I hope these things are clear to you people. So this was actually the typical finite element for this element. So this was node 1, this was node 2, so it was having velocity u1 here and u2 here. Okay, u2 here, and it was having a length of L. This was a typical finite element. Finite element for fluid flow. Okay, volume flow rate in each element, we can also calculate that. First, let me highlight these things that we deduced. We got this u of s, and we got our shear stress. We have now volume flow rate in each element. Volume flow rate in each element, we can write it as, it can be equal to, we have to just integrate from y1 depth to y2 depth, velocity u is function of y times dy, which will be equal to minus 1 to 1, because our element is from that one, u of s L by 2 ds, because we converted into the s coordinates. It will be L by 2 u1 plus u2, simply u2. Okay, so total volume, total flow rate, total flow rate will be just the summation of all the elements. Total flow rate will be sum of volume flow rates from each element. Okay, so it will be equal to 1 by 2 for element 1, L1, length of that one, U1 plus U2, up to, if there will be m element, is Lm, Un minus 1 plus Un. Okay, total volume flow rate. Okay, I hope this point was also clear to you. Now let us solve a problem on this. Quickly solve a problem. We have some time left. We'll solve a numerical problem on it, then we will see how things will go. So actually, what is our problem first for today? Problem is today's problem. So today's problem is there are two fixed plates like this. Okay, fluid flow between the two fixed plates will be obviously because above plate is fixed, so velocity will be zero here and zero at the bottom as well, like this. Okay, velocity profile will be like this. Okay, this is this velocity profile. Okay, so u of y is given as this. We have also the variation of the pressure along x direction. Dou p by dou x is already given from there, is it is minus 2 into 10 to the power 5. It's in pound feet lbf per feet cube. Okay, okay, and the distance between these two plates is given as 0.3 feet. Okay, and we have been also given that there is a variation of the viscosity within the two plates, like the value of the viscosity since the temperature is different at two plates, that is here T naught temperature is 80 degree and temperature at the above plate is 200 degrees. So since the temperature is varying, so viscosity will be also varying. So there is a change in the temperature like this. So temperature variation is like this. Temperature variation. So temperature at top is 200 degree Fahrenheit. Sorry, this is temperature at the bottom is 80 degree Fahrenheit. Okay, so I don't know long values here. Okay, so accordingly the viscosity will be also varying. So how we will tackle this problem is that we will divide this problem into different number of elements so that we can accommodate the variation in the temperature, so that the variation in the viscosity is also accommodated. Okay, so we will propose a three element model for this. I will propose a three element model for this, like this. So this is one element. Sorry, this is one node. This is another node. This is another node. This is another node. Okay. We will see a three element solution for our problem because there is temperature variation. We will see if we can accommodate all those things. Okay. So this is element first, element second, element third. Okay. Element third. And we have nodes 1, node 2, node 3, node 4. Okay. Uh, and the temperatures are 80 degree Fahrenheit and above temperature is 200 degree Fahrenheit. So how many parts we have? We can write the temperature to be here. We can do 40 divisions, no? 40 40 40. We can write it 120 degree Fahrenheit here. We can write 160 degree Fahrenheit here and 200 degree. 80 plus 20 is equal to 120. 80 plus 40 is equal to 120. 120 plus 40 is equal to 160. 160 plus 20 is equal to 200. So we all three values are all three four temperatures are accommodated here. And the viscosity is also varying in between these two temperatures to be. So the viscosity is like this. Viscosity mu within this element, we it is a given data actually. I'm not writing it on my cell phone. It's a given data 1 into 10 to the power minus 5. Viscosity in this element is mu to be equal to 1.25 into 10 to the power minus 5. Since temperature is increasing, viscosity is decreasing. That's a natural law. 1.25, and mu in this element is given to be 0.9 into 10 to the power minus 5. Okay. So we have a three element model. So we will directly write the element equations for the three elements, combine those to form a global system of equations, and then solve that by applying the boundary conditions. Okay. So if I directly write element equations for element 1, I'm writing this equation. I'm using this equation. I'm using this equation. Okay, mu by L, 1 minus 1 on U1, U2, dou P by dou X minus 1 by 2, 1 by 2. And for each one, you can see that L for each one is 0.1. Since hole is 0.3 feet, L for each one is 0.1 feet. Okay, for each one 0.1, 0.1, and this is 0.1. Okay. So using all these values and the element equation for each element will be 1.5 into 10 to the power minus 4, 1 minus 1 minus 1, 1 u1 u2, u1 u2 to be equal to 10 to the power minus 6, 1 1. For element 2, it is 1.25 into 10 to the power minus 4, 1 minus 1 minus 1, 1, u1 u2, 10 to the power minus 6, 1 1. Element 3, it is 0.9 into 10 to the power minus 4, 1 minus 1 minus 1, 1, u1 u2, 10 to the power minus 6, 1, 1. Okay, we have all three element equations. So global equations after assembly are, so once we assemble, we will get a global system to be equal to 10 to the power minus 4 times this. It will be like this: 1.5 minus 1.5 will be 0. It will be 0. It will be minus 1.5. It will be 2.75. You people know how to assemble the equations. Minus 1.25 could be 0. It is 0 minus 1.25. It will be 2.15. It will be minus 0.9. It will be 0, 0 minus 0.9, 0.9. Okay. And we have four variables, that is u1, u2, u3, u4. And you know that u1 is equal to 0 and u4 is equal to 0 because it is the boundary condition, that is u1 here and u2 here. Velocity is 0 at 2 points. So the whole system will be u1, u2, u3, u4. Okay, to be equal to 1, 2, 2, 1, 10 to the power minus 6 is outside. So applying the boundary conditions, that is, I already told you the boundary conditions are u1 equals u4 equals 0. The reduced equations are reduced equation will become 10 to the power minus 4 2.75 because u1 and u4 are 0, so we have to do the tactics like the same. So we have to cancel this row, this column. We have to cancel this row and this column. So our remaining things that we will be capturing will be only this thing and this thing only. I hope you people are getting my point. That's why I'm writing the same thing here. 2.75 minus 1.25 minus 1.25 or 2.15 u2 u3 u2 u3 to be equal to 10 to the power minus 6. So solution will be u2 to be equal to 1.56 into 10 to the power minus 2 feet per second, and u3 to be equal to 1.84 into 10 to the power minus 2 feet per second. So the velocity distribution will be like this. We had three elements. We had one here, one here, one here, and one here. So we have fluid flow of 0.0156 feet per second here, and we have fluid flow of 0.0184 feet per second here. So the fluid profile will be like this. Okay, I hope this point is clear to you people. Then we can calculate other things as well. Get calculate shear stresses. Okay, shear stresses. So shear stresses at bottom of plate from element 1. So that is tau xy will be equal to 1.5 into 10 to the power minus 5 divided by the h, the length of element 0.1. into 1.56 into 10 power minus 2 minus 0. This is equal to 2.34 10 power minus 4 units. Okay. Similarly, at the top plate from element 3, bottom plate, top plate, top plate, I will directly write the value tau xy to be equal to minus 1.66 into 10 to the power minus 6 units. Okay, I hope this thing is clear to you guys. You got all the quantities, and now we are left with only one quantity, that is the total volume flow rate. Total volume flow rate. So total volume flow rate is equal to, I already told you, it is the summation of the volume flow rates in each element. So it is 1 by 2, 0.001. I will directly write the values by using the formula 0 plus 1.56, U1 plus U2. Then it is L2, 0.001, U2 plus U3, 1.56 plus 1.84. Then it is 0.001 U3 plus U4. 1.84 is U3, U4 is 0. 0. So it comes out to be volume flow rate V is equal to 3.4 into 10 to the power minus 3 feet cube per second feet. Okay. So this is the value we got. So we can increase the number of elements from 3 to 4 to 5 to 6 to have a convergence in the solutions. As you people can see that this is a weak profile, weak approximation, as the number of elements is very less. If we increase the number of elements, this approximation will become very clear like this. Okay. So we can use a different number of elements, higher number of elements. That is, we can write a computer code for it by using 6, 7, 8, 9, up to 30 number of elements, and we can smoothen our results to get more precise results. So I hope today whatever we studied is clear to you guys. So thank you everyone for joining this session. Today we saw the general boundary value problem and its application in fluid flow. Can you please mute your mic? For we saw general boundary value problem like this. We saw that all the general boundary value problems are linear in nature and they are second order differential equations, and their general solution is given as this K and R. And then we saw how this general boundary value problem we can use in other applications like fluid flow between two flat plates. That's the lubrication problem. We deduced the governing differential equation for the fluid flow problem as well, and then compared it with the general boundary value problem and got the values for the element equation, or we got the element equation directly. That element equation, we got velocity profile, we got the shear stress, we got the total volume flow rate, and then we solved the problem regarding that as well. One full-fledged problem on that. Okay. So thank you.
Danish, one question is gonna ask.
Okay.
Yeah, this from the week 10 lectures of from the sir's lecture videos.
Okay.
Can I ask? Yeah. So actually, this sir has explained about finding out the shape functions for six-noded triangle, that is linear strain triangle.
Okay.
Yeah, but I did not understood how to find out the middle node shape function by using this Lagrange polynomial.
So we will be coming on those higher order shape functions for the triangular elements, quadrilateral elements, and maybe in a couple of weeks I can make you understand at that point of time.
Okay, because assignment there are many questions. This present assignment is having 3-4 questions on that.
Because we are going to study, I think in coming week or the week after that, we will be studying
Okay,
triangular elements and quadrilateral elements, maybe.
okay, right.
Okay, thank you.
Okay, thanks.
Okay, thank you.